We are going into lecture number 9, where we want to discuss microprocessor programs. Let's first define the terms machine code and source code. Machine code is a program that is made up of a sequence of binary coded instructions. Microprocessors can only run programs that are in the form of machine code. So this means that the applications that run on your computer or on your phone or on any other programmable device are in the form of machine code. However, it is difficult to develop programs using machine code. So as a result, a number of programming languages were developed over the years to help ease in the development of computer and microprocessor programs. So some examples of these languages are assembly language, which is a low-level language, then C language, C++, C Sharp, Java, VB, Python, etc. And these are high-level languages. Now, a source code is a program that has been written using a programming language. So in order for the source code to be able to be executed by a microprocessor, it has got to be changed into machine code. Right, our discussion of microprocessor programs is going to be based on assembly language so that we understand how the microprocessor works. An assembly program is a sequence of assembly instructions, and normally that sequence is developed to perform a certain task. We have an example of an assembly language shown here. The first instruction reads the number on port 05 and stores it in register AL. Then the next instruction adds 7FH to the number that is stored in AL. So this will be equivalent to adding the number 7FH to the number that has been read from port 05H. Then the third instruction stores the number in AL in memory pointed to by BX. So effectively, our program has read a value from an input port, added a constant to the value read, and then stored the result in memory pointed to by BX. The last instruction, which is out, is we have just used it there to stop the program so that it does not wander off. A second example is a program that calculates power given current and voltage. In our example, voltage value is in register BX and current value is in register CX. The power value is required to be stored in memory and starting at address 1800H. Let's look at the program. In our application, we need to make use of the multiply instruction. We note that in the 8086, the multiply instruction multiplies the value in the accumulator by a value in n of the GPRs or a value in memory. So we would need to move one of the values into the accumulator. So the first instruction moves the value in BX into the accumulator. So we move the value of voltage into the accumulator. Then the next instruction multiplies the value in accumulator by the value in CX, which is effectively multiplying the value of voltage by the value of current, and that gives us the value of power. Now the product that results from a multiply instruction is stored in a register pair formed from registers DX and AX, where DX is the higher weight and AX is the lower weight. So which means our value of power is stored in the register pair DX AX. So the next two instructions which are move instructions are storing the value of power in memory. And with those instructions, it means our value of power is going to be stored in memory that starts at address 1800H and ends at 1803H. So 1803H is going to store the highest byte, while this 1800H is going to store the lowest byte. A label is a symbolic name for the memory address of an instruction. Each instruction in memory has got an address. We can decide to give a symbolic name to the address of a particular instruction in the program. That symbolic name is what we call a label. Labels are used to enable referencing to addresses of instructions. For example, when a program needs to branch. In 8086 assembly language, labels are indicated by placing a colon after the label. We have got here an example to illustrate the use of labels. It is a program that continuously reads a port until a non-zero value is read. Let's look at the program. So the first instruction is labeled. So the label is NP loop, and that NP loop is the symbolic name for the address at which the instruction starts. And this first instruction reads port 04H into the accumulator. The next instruction is the one that is used to check whether the value is 0 or not. So it's a conditional jump if 0. So if the value read in the first instruction is 0, the program execution will branch to the label NP loop, which effectively is a branch to the first instruction. If the value was non-zero, then the program is going to proceed with the instructions that follow the conditional jump instruction. Another example that can be used to illustrate the use of labels in programs is a system that switches on or off streetlights depending on light intensity. The system is made up of a light sensor that senses the light intensity and converts it into a signal that is going to be applied into an ADC. The ADC will change this signal into a digital signal, and the output is an 8-bit value that is applied into port 08H. Then the street lights are connected through to port 0AH, and they are connected through relays. So the port is going to switch relays, and the relays in turn are going to switch the street lights. The threshold light intensity is C5H. This means that when the value read from the light sensor is above C5H, it is bright enough, and therefore the lights must be turned off. If the value read is below C5H, it means it is dark, and therefore the street lights must be put on. Then the other components are the components that will be required in a microprocessor-based system for it to be able to run the program. Here is the program that will be required to run the system. The first instruction reads the light intensity through port 08H into the accumulator. The second instruction compares the read light intensity to the threshold value. The third instruction is a conditional branch instruction. Depending on the result of the comparison, it causes program execution to branch to the code section that is used to switch off the lights, or to the code section that is used to switch on the lights. Here is how it works. If the light intensity is above the threshold value, the conditional jump instruction causes program execution to branch to the instruction labeled light off. So the instruction labeled light off loads the code 00H, which is the code used to switch off the lights, into the accumulator. Then the next instruction writes the accumulator to port 0AH, and as a result turns off the lights. If the light intensity is below the threshold value, there is no branching. Program execution follows the natural sequential flow. So the instruction that follows the conditional branch instruction is an instruction that loads the code 0FFH into the accumulator. So the code 0FFH is the code that is used to switch on the lights. Then after that, the accumulator is written to port 0AH so that the lights are turned on. So the reason why we first of all load the codes into the accumulator before writing to the output port is because we do not have an instruction that allows an immediate value to be directly written to a port. So after each code section, there is a need to branch break to the first instruction. So after each section, there is an unconditional jump instruction that causes jumping to the instruction labeled start, and that instruction is the first instruction. So this allows the program to run in cycles so that we can continuously monitor the lights and correspondingly turn them on or off depending on the light intensity. Comments are included in assembly programs to improve the readability of the program. For example, they may be used to describe and explain uses of particular instructions or uses of particular code sections. So the comments are not changed into machine code. In the 8086 assembly language, comments are preceded using a semicolon. We have an example of a program that illustrates the use of comments. The comments in this program are used to describe the use of the instructions and therefore the purpose and the function of the program. To illustrate further on comments, here is the street lights program with comments. So the comments basically are just describing the purpose of the instructions and overall indicate how the program works. So like we said, the comments themselves are not turned into the machine code, only the program. So the program inside the blue boundary is the one that is going to be turned into the machine code. The comments that are in red are going to be ignored. Flowcharts can make the development of programs to be easier and simpler. They can also make the presentation of algorithms to be clearer and easier to understand. It is therefore recommended to use flowcharts in the development of programs, especially for complicated problems. The design process then involves first developing the algorithm in the form of a flowchart and then turning it into a suitable program. Let's illustrate the use of flowcharts in the development of programs using a program that copies a block of data from one block of memory locations to another block. We can call it the copy and paste program. The source block starts at 4000H, the destination block starts at 6000H, and the 1000H items are to be copied. Here is the flowchart for our solution. The idea used in this solution is to have two pointer registers. The first pointer register points to the first location in the source block. The second pointer register points to the first location in the destination block. We then move the item in memory location pointed to by the source pointer to the memory location pointed to by the destination pointer. After that, we increment our pointers. We then repeat the process until all the 1000 H items have been copied. The flowchart indicates that the first thing that is done is to initialize our pointers as well as a counter register. The counter register keeps track of the number of items that are still to be moved. The next thing will be to move a single item from the source block to the destination block. After the move, we increment our pointers, and after incrementing the pointers, we decrement the counter to indicate that we have moved one item. After decrementing the counter, we check if the counter is 0. That is, we check if we have moved all the items. If the counter is not 0, we execute a loop. So we continuously go through the process of moving an item from source to destination until the counter goes to 0. When the counter goes to 0, we exit the loop, and that will be the end of the program that moves the data from a source to a destination. Right. We also put labels in the flowchart. So the labels are put at points where there is a junction, like at this point, move next. They are also put at points where we've got two alternative pathways. So fortunately, in this flowchart, the alternative pathway is directly connected to this junction. So if there were some blocks before we get to the junction, we're going to put in a name on one of the alternative pathways. This is the program for our solution. The first three instructions initialize the pointers and the counter. The next two instructions are used to move a single item from the source block to the destination block. We note that we first of all move from the source block to the accumulator, then from the accumulator to the destination block. The reason why we do so is because we do not have an instruction that allows us to directly move an item from one memory location to another. The next three instructions are used to adjust the pointers and the counter. The next instruction is a conditional branch instruction. The conditional branch instruction allows us to execute a loop for 1000 times. And when you execute it for 1000 times, it means we would move 1000 items from the source block to the destination block. That is the commented program. Before proceeding to the next section, I will recommend you to attempt these two questions. The questions are found at the end of chapter 5, and these questions are meant to make you practice writing programs.